All right, welcome to the stream. So today I will be focusing on improving the audio on the NES emulator and also try to get the glitch-free video rendering, like without any tearing. So a smooth 60 FPS perfect frame rate. That is the goal. We'll see if we get there. I think performance-wise it should be possible. So, yep, I preloaded an open source ROM and we can try it out. So let me know if it might be a little bit bad audio perhaps, but let's try it out. All right, so that's how the audio is right now. It's a little bit glitchy, so that's what I want to improve. And let me know in the chat if you were able to hear it and if it sounded okay or horrible, if the volume was okay and so on. I hope it wasn't too bad. All right. So maybe I should clean this up a little bit. Because none of this is being used anyway. So what we have here is a memory region where we can store code and data that doesn't fit on the internal flash. And the way we do that is that we store it on the external flash, and then in the main function, we copy the actual data into the RAM. Usually this is handled in a startup script. Let's see here. It's basically what's being done here. So with the initialized data areas, where you have like a global, or when you have variables that have a defined initial value, they're being defined like this. So all the pointers that point to them, all the references, they point to the RAM areas, but the actual content is stored onto the flash. So in order to get it from the flash to the RAM, you have this in the startup script where you copy the data. And this is written in assembly, and I'm not that good at assembly, so I just write it in C instead. So I just made this super ugly hack. So the way it works is that these variables, they're imported from the linker script, where we define a few symbols. So this symbol points to the location in Flash where it can copy the data from. And then this one is where in the RAM it's supposed to go. And then this is where the data section is. And this is the length, so how much data to copy. So it will just take the end to the beginning. So it reads from the external flash, stores it into the RAM, and the length is the difference between this point and this point. Make sense? I hope it makes sense. So the reason why I have this array is because these magic symbols are not always easy to print. Like, I can show you. So, oops. Oh, it doesn't build anymore. I guess I screwed something up. Probably some missing semicolon or something. What did I do? All right. I deleted a little bit too much code. There we go. Nice. Yeah, so all right, it will try to debug or attach. Yeah, so if I try to print this symbol, for example, it works. I get an actual pointer. That's nice. But if I print this one, yeah, it happens. GDB crashes. Nice. So that's kind of annoying. So that is why I did like this. So if I go to here and say, yeah, right. Now I'm actually not running the same code, so it doesn't make sense. Yeah, exactly. Take a shot every time GDB crashes. Yep, that's nice. Yeah, so anyway, that's the reason to why this code looks like it does. And these comments aren't really true anymore. Yeah. that's basically it. Yeah, so what this code does, it copies it from flash to RAM. And yeah, right, this code is there to check if the flash driver is completely broken, I think. So we can leave it. I guess we can actually commit this code. I'm just gonna run it again. So after I made the changes, oops, there we go. So I made some changes to the flash driver yesterday, the flash loader, and actually I can go through what I did really quickly, like a recap from yesterday. So the main reason to my changes yesterday were to support the large flash. And to do that, I needed to rewrite the driver a little bit. I don't like the initialization. This is annoying. Let's do like that. Yeah, so what I did was I created this init function where you take which quad mode you want to run in, either quad or SPI mode, and then which vendor your flash is. Good morning, Digester. So here we do some logic. We disable quad mode in case we are ISSI driver, and then we do the reset, and then we enable quad mode if we want quad mode for ISSI, because the MX vendor doesn't support real quad mode. It only has quad SPI commands. So anyway, this sets two global states in the flash driver, so that the next calls we do will be aware of the quad mode and vendor. I don't understand why this doesn't work. I can't control click. Anyway, yeah, so maybe this can be cleaned up as well. So we have defines for the commands. But anyway, it will send commands to enable write. And depending on the quad mode that we get here, we will select a different configuration, basically. So here we want, we also tell this in case we have data or address lines. So if we go to that definition, this time it worked. Yeah, so here is some logic where we check if we are in SPI mode, we want a single line instruction. And if we have an address, then we use a single line address, otherwise none. If we have data, single line, none. And then for quad mode, for MX, it's not actual quad mode, it's SPI mode with quad address and data. And that's what we do here. We have a single line for instruction and quad or none for address and quad or none for data. But for ISSI, we actually do have quad mode. So we want to use the quad lanes for instruction. So that's what this code does. And yeah, I reuse that everywhere. So I hope it's a little bit easy to read. It's a little bit hacky though, because here, for example, we do a check if we are in quad mode and MX, then we should still use the for pp command and not the pp command, because pp can, this only works in SPI mode and in quad mode. But since we don't have quad mode for vendor MX, we can't use it. So that's why it is like this. So yeah, I tested this a lot yesterday, and it works really well. So we have this flash.sh script, which I improved quite a bit. So I have added some exported persistent variables. So the way this works is that I have a RAM section in the linker script that I call persistent, like so. What this does is that this will not be initialized when you boot the microcontroller. It will stay the same. Like if you boot and set a breakpoint in main or whatever, your variables that are stored here will not be reinitialized to 0 or whatever. They will just stay whatever is in the RAM at the current point in time. So what this enables us is that we can use these as an interface between OpenOCD and the Flash script and the program. So in the script, I rip out the addresses to those symbols, and then I reset it. I program the elf, I reset the microcontroller, and now we are basically in the so we have loaded the new firmware, and we are in the startup function in the very beginning. And at this time, we load what we want to flash into RAM, and we write to these special variables. And then we do resume. So what this does is that in the very beginning, the microcontroller is halted in the startup. It will be populated with these variables. So when we enter main, all of these variables will contain the data that we have written to them. So this is our interface. So what this enables us is that we can, from the script, tell how much we want to write, where we want to write it to. I also added a magic. Magic is there so that you don't accidentally flash stuff. So for example, if you unplug the power and you connect the power again, the program will execute, and without the magic check, it will start overwriting your flash and just killing it, which is no good. So that's why I added the magic. So what we're doing here is that we write a magic value that we know. So it's a special value. Then we check that value here, and then we continue. And then, yeah, we set it up, and we write, we erase, we program. And then finally, we set the program done variable to cafe food, just another magic that we then check for here. So this little loop, it queries the microcontroller, what is the value of program done? And then if program done is cafe food, then we say, oh, it's done, and we break, and it's done. So this way we can actually have a script that that blocks until it's done. Yeah, so much about the flash loader. Right, so I also wrote another script that uses this to flash multiple 1 megabyte chunks. So here we split up. This is sort of ugly bash, I'm sorry, but yeah, it works. So what it does is it copies 1 megabyte chunks into a temporary file, and then it calls the flash script, and then it moves on to the next chunk and next chunk and next chunk until it's finished. So the only downside here is that this takes time. It's not very fast. It is what it is. But if you have a fast programmer, this will be faster. It's limited by the speed of your programmer, basically. Yeah. So that's it. And I tested this with like a little bit larger and a little bit smaller than even megabytes. So, and it seems to work. I don't leave any guarantees, of course, but it seems to work. I did some testing, so I hope it doesn't break at least. Yeah, so enough about that. So back to the emulator. So we can just see if I broke it. Right, I need to connect power. So what I have here in the emulator makefile, I have this flash xmem where I simply have the binary as a dependency. So it will build all the files to produce this binary, and then I call the flashloader script with the external flash binary. If soldering isn't an option, what would be an alternative way to flash the Game & Watch? Well, you don't actually need to solder if you don't want to. Like, let me see if I can find a good picture. Just 1 second. So the SWD pins they don't actually require you to solder because they're exposed pads. So you could use pogo pins. Oh, there has been so many tweets, I can't really find the original thread anymore. It should be here somewhere. Yeah, here we go. So let's do like this. Ah, damn it. Why can't I find it? Ah, here we go. Okay, so this is basically it. These are the exposed important pads. So what you can do is we could design like a simple pogo pin adapter where you simply hold the pogo pins against these connectors. So just to illustrate what a pogo pin is, in case you don't know, it's a spring-loaded pin that you hold against the PCB. So it connects even if there is no connector. So when there is only exposed copper, it will still make a good enough connection. But the downside is, of course, that you need to hold this down until the flashing is completed. And that can take a while. But it doesn't require you to solder. So we could theoretically build a simple PCB with pre-soldered pogo pins that you simply hold against the connector. So that is something that we could do. Aren't those fairly expensive? Oh yeah, test clips are a little bit more expensive. Yeah, so this PCB solution, like a simple PCB with pogo pins, that would be like a few, like $1-2. Like it can be extremely cheap. Like you can get the pretty crappy pogo pins from AliExpress, but they will be like good enough for this purpose. So I think if you just want something, you can do it. In order to enable people who really don't want to solder, we can do that. That's no problem. All right, so going back here, I was flashing it. Right, I'm gonna flash the external or the internal flash, and yeah, it seems to start again. Yeah, and the sound seems to work. Shame there is no data over USB by default. Yeah, definitely. Yeah, it's really sad. Yeah, I agree. This really raises the bar for modding, for sure. All right, so going back to the code, yeah, I guess I can commit this cleanup because I just removed some stuff. Yeah, let's do that. Yeah, you're right. Yeah, it's most definitely because they want to prevent people from tinkering. But yeah, just learn to solder. It's not that hard. But at the same time, I can understand if you don't want to do it, or if you don't, if you can't do it. But yeah, so that's why I'm mentioning the pogo pin solution, because that is not that hard. And if you're willing, you can even drill a hole here, and then you can just plug the pogo pin through the case. But of course, it's not elegant, but you can do it. It's not. It's possible. All right. Yeah, no, I can understand that you don't want to go and solder the USB-C pads. 'Cause I was working under a microscope and I still struggled. Like it wasn't. It was pretty. I don't know. I really don't like to solder lead-free because it's a pain. So I don't know if everyone saw it, but this is what you have to solder. So this is the USB-C connector, and these are the wires. And it's really easy to create bridges here, and it's also a little bit, with the magnet wire, it's always a little bit, you know, finicky. It's not always so easy, but it can definitely be done. Get something else for training and good flux. Yes, that's a good tip for sure. I can do a live today for this soldering group. Yeah, let's do that. The more people who know how to do it, the better. All right. Um, am I blind or? There we go. I couldn't find the entry point for some reason. But there we go. Back in business. Oh, crap. So pro tip, don't press Control Q. It will quit Visual Studio Code. All right, so going through the architecture here, we have a DMA buffer for audio, which is a circular buffer, so it keeps looping. So we initialize it with an empty buffer, so it plays silent sound all the time. And then we have a callback. Whenever the DMA job is done, we get this callback. Right now this code is kind of horrible because it will copy from the second buffer into the first buffer inside of the interrupt context, which you should really not do. But this was a quick hack for bring up, so yeah, it worked. So that's what we're gonna fix today, I think. Yeah. Yeah, so for USB, I don't know. There are so many different solutions you can do. But yeah, the big problem is that the native USB is shared with the LCD. I think that might be a showstopper, because yeah, I don't know, maybe not. I do have another modded unit which I can try out later, but I don't have it with me right now. It's in the lab. But I think we can actually try to write some very simple tiny USB, or maybe even using STM32 HAL, and just get like a what's it called? A UART, basically, CDC, just to see if the USB lines actually work. All right, so going back to the audio stuff. Yeah. You can actually read the documentation. Even if the documentation is usually not really accurate, it might give us a hint on how it works. So right, and that is what I'm doing. So we are using this function. Okay, so with this abstraction layer, or with this abstraction, there is no way to get the half full. So I need to hook into that myself, I think. So if we look at how the HAL calls this callback, it does it. All right, okay. So this is probably the one we care about. So when the DMA, so the SAI has hooked into the DMA transmit complete callback. And after it does its own state handling, yeah, it will call the user callback. So where does this come from then? So here you can actually see that there is actually a TX complete and TX half complete. So that's interesting. Okay, so what does this do then? Oh, so there is actually a SAI. Okay, it was just not documented. Okay, cool. As always. But that's fine. Let's not be angry. Let's just add another. So the way you implement these callbacks is that they have stubs implemented with the weak prefix. What weak does is that it lets the linker find this stub implementation, but if you also implement it, the linker will choose your implementation over the stub. So this is cool. Here we get the tx off. Yep. So let's create some global variables. Let's call it DMA state, and let's move this here. We can change this to enums later on. So we will flop between DMA state 2 and 1, right? And we don't want to do this mem copy, we want to solve it nicer. So what do we actually want to do? I guess if the audio buffer is twice as long as one video buffer or video frame, so if we sort of draw a timeline, so if these are the video frames, I'm really bad at drawing, but basically that we can update basically that an audio frame is twice as long, so basically this long, and when we reach this point we will update this data. So when we start playing, the video and audio will be in sync, and it will play this part of the buffer, or actually the other way around. So if you have a buffer, we can have it split, like so. So in the beginning, we play actually the second part, and when we reach this half part, we will update this part, so that you always, maybe the best thing is to keep the audio lag half a video frame behind or something, so that you're always low latency, but you still have a full buffer that you can play. I think that's how I'm gonna do it. I'm sorry for the horrible illustration, but let's see if we can do it. So this will be called from the, let's see here, from NES, right? So NES emulate is sort of a infinite loop. So this is the main loop actually. So we do get input, render frame, and what render frame does is it actually runs the emulator, or actually it runs the video chip basically, and after that it will run the CPU, and when this is done it will have updated the pixels in the frame buffer, and then in case you have a slow computer or slow microcontroller, you might have to skip frames, and that is what's being controlled here. So if you want to skip a frame, then this will not be called. This will save some time and enable you to catch up. But our goal is to never skip frames, because skipping frames is kind of lame. It will look bad. So let's see if we can handle it without it. Okay, so after we have rendered the frame and put it on the display, we will execute or emulate the audio chip. So the audio processor will, depending on its internal states that have been updated from the CPU, it will create samples into our audio buffer. And so now the audio buffer contains a number of samples. I think. Right, it's actually, this is the one that we're using. Yeah, right. So this is basically just a callback into our integration layer. And we call the APU process and request buffers into our buffer. Yeah. And then what we have to do on the Game & Watch is that we need to lower the volume because it's kind of funny. It draws so much current to play loud audio that the whole board dies. It browns out. It uses too much current, so it just dies. So the overcurrent protection kicks in and just... Oh no, we have spammers again. Yeah, let's hope that worked. Okay, cool. So now we know how that works. So again, this is the main loop. So after we have jumped into our integration layer and we have requested audio buffers, we still don't have to do anything. We have just prepared audio buffers. We don't, I mean, we could theoretically write into the right buffer at this time, and then OSD wait for vsync. This is basically the end of the loop where we can catch up and wait for audio and video to come and sync. And right now I don't think I even do anything. Right, so this is handling the frame skip, which I don't think we should do. We can probably remove this, but it's good to have it in case it's needed. Because most of the time it shouldn't really skip any frames. So I think I added a print. Yeah, exactly. So every second we will print the average FPS, rolling average the last second, how much we manually slept, which we should remove, how many frames we rendered, and how many frames we skipped. Yeah. How does Twitch not have spam and control? Yeah, so I did a quick Google on it, and then there seems to be something called automod, and I guess I have to activate it, but I don't know how. I'm a total noob when it comes to Twitch. Let me see. Block hyperlinks. No. Links are good. Okay, a little moderation. Okay, let's bump it up. Some moderation. Yeah, I've increased the automod to some moderation. So I don't know. Maybe if the machine learning thinks you're writing something bad, a moderator or me has to approve it. But I hope it doesn't have to. We don't have to do anything. Let's see. All right. So I can show how this works. So I have this thing called logbuff, which is a circular buffer, which it's not a fancy buffer. It just resets. And what it does, it just writes the whenever you use printf, it writes it to this buffer. So it's really fast. It doesn't cost much. It just costs a bit of RAM, and but the downside is that you can't see this in real time. Potentially, you could have like a OpenOCD plugin or like a script that just pulls this all the time, and then you can have you can see the logs in real time ish. But I haven't done that, and I don't intend to do that either. So now it seems that we have 69 frames per second. Very nice. I don't know why it's so even. I guess it's this menu that's just very constant in cost. Yeah, but we seem to be managing. All right. I don't know if you can hear any music, but it's a little bit annoying because sometimes the DMA gets stuck and it's just quite annoying. So I hope I spare you from that. Anyway, let's look into the code and see if we can improve this. Yeah, I don't know. Coding while streaming is perhaps not the most efficient way to do it, but I don't know. I like to share the process. Why not? Because all of this is kind of fun. And maybe someone doesn't know how to code or is curious. So yeah, this is how it works. So anyway, here we have the DMA states. So what do we want to do with those? So I think I should increase. So yeah, this is hard coded to NTSC. So later on, we can rewrite this so it works in both 50 and 60 hertz. But for now, it's just hard coded. And audio sample rate divided by 30, that means that we have room for 2 video frames of audio. And the idea is that we should use, yeah, let's think a little bit. Yeah, I should just put this print back because I don't remember if this actually worked or not, if we got the correct number of samples or not, because there was some issue about that. I think I got like 800 before. So I'm just gonna open up a Python console. It's always nice to have. So we should get 800 audio samples per frame. And if we're running at, yeah, if we want twice that amount, that's 1600. So let's, yeah, let's think a little bit. So we want to ask the APU for 800 samples, but we want the DMA transfer to be 1600 samples. Accuracy of this particular NES emulator. Yeah, well, yeah, I guess so. If you want accuracy, you can use, I always forget the name, BNES, BSNES. But I don't think that will be able to run on this microcontroller. If you want real accuracy, you probably want to run on an FPGA. But that is a completely different chip. But that would be a really cool thing to do, like a replacement PCB board with an FPGA that is actually cycle accurate. That would be really cool. Higan, yeah, exactly. And from what I've heard, that one is like the best. But I don't know much about the emulation scene, and I might be swearing in the church. I don't know. But from what I've heard, that one is supposed to be. Oh, okay, I see. Oh, okay. So for NES, is there some emulator that is like the gold standard? But in any case, I don't know, but I don't think that any cycle accurate emulator will be able to run well on this hardware platform, but I don't know. And I'm happy to be proven wrong, because having that would be really cool. But yeah, my goal was to port something that looks decent and works. Having 60 FPS is more important than having it cycle accurate, because if you drop frames, it doesn't matter, right? Fewness. Okay, cool. Thanks for letting me know. Because all of these, I mean, I played on emulators like 10 plus years ago and haven't really cared about emulators for a long time. So it's kind of interesting to see what's happening. Like there are so many different implementations. It's really cool, uh, but it's also a jungle. It's hard to know what is good and what is bad. So again, let's just flash and run this so we can get some prints. So let's see what we do. The audio buffer length. Yeah. So maybe I should actually do like this and have a single DMA buffer that is twice that. Like, yeah, maybe this is cleaner. Yeah, let's do like this. Yeah. So we have two buffers. One is what is being produced by the emulator, and one is what the DMA job is running. I think that would make sense, yeah. And the DMA job is twice the length. Right. And then we write into the DMA buffer and we go from 0 to audio samples. And then we write the emulator data into the DMA data. We shift it down, and then we should have an offset. And the offset is either based on DMA state it's either 0 or audio samples, which is 800. So it's either gonna write to the beginning or the middle and forward of that buffer. So the question is, where should we wait for the next DMA state? So yeah, I think this should work. But the thing is, what happens if we are not in perfect sync? So I mean, we should probably do the synchronization in the vsync function. And instead of sleeping, all right, that's also removed. What did this do again? Oh yeah, that doesn't do much. Yeah, let's just remove this for now. Actually, we can remove everything here. And then just do okay, it builds. That's good. This might sound horrible, but let's see what happens. So it doesn't sound perfect. There is some crunchiness, right? But it doesn't sound horrible either. But there is something funky. Let me record. I hope the stream doesn't die because I'm running Audacity now. I'm gonna record a little bit. Okay, so let's look at this together. Just gonna kill the emulator. Okay, so first of all, I guess we can cut that away and normalize. And what do we see? Okay, this is audio, so I guess ideally we should have like a scope. The SLAI logic has analog inputs, but I think the voltage is extremely high, so I tried to record before, but it didn't really work. But there seem to be like these harsh waveforms. I don't know. There's nothing that looks really bad. I would have hoped to see something obvious in this. There seems to be a lot of like spikes. If anyone have any, or if anyone has any ideas or suggestions what I can try, let me know. Yeah, maybe I'm doing something completely wrong here. Let's try to swap the polarity of that one. See if that works better. I think I can do this now. Oh, I think my thing just died. Yeah, my external mic seems to have died, of course. Here we go again. So this is how it sounds. Okay, perhaps try recording at a higher sample rate and see if the spikes are periodic or more obvious. Yeah, that's a good suggestion, thanks. But yeah, this is how it sounds. I'm just gonna mute. Isn't the mic here? Yeah, so I'm not very good at writing to the APU, but I guess one thing we could do is to do what you're saying, make a periodic tone, just turn on the triangle wave or whatever, and look at the waveform. This doesn't look that bad, right? Maybe... well, let's see if we can do that. So I guess if we write into the APU ourselves, so triangle enabled. This is kind of funny. I've never actually done this, but I guess we can try to hack it just by going here. So we say mess get pointer, and then we do mess.apu, and then we can turn off all of the... we can turn off everything and only turn on what we care about. So rectangle 0. Oh, that's a macro. How nice of them. Okay. APU rectangle dot output volume. Okay, cool. So let's set the output volume to 0 on everything. So we have the two rectangles, and then we have, let's see, do we have more? We have triangle, we have noise, and then we have DMC. I honestly don't know what that is. I'm not that familiar with the NES audio. Ah, emulator test. Nice. Ah, thank you. This is, I'm just diving nose first into this. I've never done anything with this. Okay. APU test, APU. Square timer, test APU. Play tones on all channels to show their relative volumes. Okay, that's nice. Oh, is this like a NES ROM that I can just load and run? For APU test. Oh, maybe that's what you told me to actually care about. You need the section called APU test. Yeah, okay. Yeah, okay. APU test. Test many aspects of the APU that are visible to the CPU. Really obscure things are not tested here. No, but that's fine. I only care about playing a single tone, like a continuous tone. So maybe I should take that one instead. Then I can just... Let's do this later in case we have to. And then let's unzip APU test. Oh, holy shit. That was a lot of files. And it extracted at least into a folder. Thanks for that. Okay, APU tests, ROM singles. Maybe I should read the README. That usually helps. We can hear you through the tube. Oh, sorry. Sorry, I forgot to disable it. Yeah, okay. Jitter length time. Isn't there like a basic test? Verify all length table entries. Okay. the length counter. I don't want. It should be a basic test. Would have been nice. Well, I'm just gonna try one. And fairly certain the length is supposed to be in 2 places. What am I missing? Oh well, let's run this. Right, let's use something else. I forgot about this. Damn it. Oh. Yeah, if you have bad make files, make sure to always clean and build. And this is an open source ROM, so should be fine. Yep. All right. It seems to crash. Doesn't look very nice. I wonder why. Yeah, this one. Cart ROM length. Oops. Hello. Here we go. This is the file that I was looking for. Okay. And here we could should use this length. So we're currently testing the audio, and I'm using APU tests from NESDev. So it's kind of interesting. Oh no, I was too fast. Oh, or maybe this should work. No, I don't know, maybe the ROM is too special for this emulator to work. I honestly don't know. Maybe we should just go back to the tilt ROM again, just because this is something that works, and then I can change. and that. By the way, not always open source means permission to use, and there's plenty of public domain ROMs without sources in Homebrew. Okay, JSTH, if you have any suggestions, please post, because I have no clue about this. I use this ROM, Super Tilt Pro, because it was on GitHub, and it was do the fuck whatever you want license, I think, which I interpret as pretty permissive. Did you build the emulator? No, I did not. I am reusing an emulator that was ported to the ESP32 called Odroid, or RetroGo, or NoFriendo. It's sort of a chain of forks and modifications. I honestly don't really know where the source is coming from anymore, because there are so many layers of rewrites, I guess, or portings. But yeah, NoFriendo. Let's see. But yeah, JTH, if you have any suggestions on a public domain, do whatever you want styles of ROMs. That's actually NoFriendo. Okay, cool. All right. So NoFriendo is the actual source, and then it has been ported to the ESP32 in the project called RetroGo, which has an abstraction layer called Odroid, I think. Trying to figure out how all of this is tied together. Like, I basically just took that code and bashed at it until it worked. Yeah, so that's where we are at right now. Okay, now we're back here. We should, yeah, that's the ROM, not that one, that one, yeah. And I will do this, and let's flash it. So it would be nice with a smaller ROM, because this one is huge, 500K. Okay, let's flash it again. Oh, I think I broke it. It looks permanently broken now. Damn it, what did I do? Okay, I have to revert some stuff. But this doesn't make any sense. Okay. Okay, it seems I have broken my device. I don't know what is going on anymore. Why doesn't it work? Oh no, the flash is sad. Why would it be that? No, it's something is wrong with the flash driver. Maybe if I power cycle the device. No. could be that I have broken some wire, but I don't think so. Let's take it a little bit slowly and see if I can access the flash with the flash loader. So, oops, let's make clean, and then yeah, so I'm gonna flash a counter. It's 1 megabyte of just 0, 1, 2, 3, 4, just as a reference. Like so. Here we go. Okay, so this indicates that the firmware at least thinks that it's flashed correctly. So I'm gonna start a debugger and open up GDB and just... No, it is actually borked. What the heck? This would be really sad if my device has finally given up. I mean, I could rip this apart and solder the chip back on. I don't... It's really hard to see because I don't have a microscope here. Damn. Because it worked so well, this hack. But yeah, it's really... I'm using magnet wires to connect the PCB to the external connector. What's your flash? Yeah. Good point. I'm gonna lower it. Clock prescaler. I'm gonna lower it down to 4 and see if it works better. Let's do it again. Original flash also couldn't be read with this. Well, that is the point of this project, to use SWD to access the external flash without any soldering. That is the point. But for some reason, it just stopped working for me. And because I have made hardware modifications, I am suspecting that it's my fault. That the soldering has given up or something. I don't know. So let's... Nah, this is no good. God damn it. Where is that? Okay. I was doing so much with this yesterday, and I'm using the stock flash and not the MX flash. Let's go back to SPI mode and see if that works better. What's the device soldered? Yeah, so yeah, I'm not sure if it's a good idea to do this, but I'm doing it anyway. So let me switch to the full screen. Okay, so I don't know if you can see, but instead of the flash, I have a piece of wire. I have 8 wires that are soldered onto an adapter board. And the adapter board has the flash. So I can disconnect this and connect it back in. So I can use an external programmer without any problem. So up until now, basically, I have been using this and it has worked really well. So I don't know why this just suddenly stopped working. It's, yeah. Question is, what has given up, Flash or contraption? Yeah, no, I don't think the Flash would have given up that. Yeah, I mean, sure, nothing is impossible, but I would bet that yeah, my soldering is probably giving up. Because this is magnet wire, really, really, really thin. I had this for hours when I started with the Flash stuff. Yeah, yeah. I just spent so many hours yesterday uh, in this code base improving it, and I never had this basically. You could set it to 100. Yeah, so I did actually that here. I set it to SPI mode. So let's try that. Let's connect everything again. There we go. And oh, I have the wrong view. There we go. So the reason why it's blinking is because I have this magic that I check for. So when you power on the device with the flash loader loaded, it will go into the error handler and protect your flash. Yeah, so when I set the quad mode to SPI mode, I initialize this one with SPI mode. And that will later lead to that this code will use the quad mode setting. So if you're in SPI mode, this will be in SPI mode. Sorry if the blinking is annoying. It is annoying to me, so I will get rid of it. Let me just restart this. Yeah, so yeah, exactly. That was what I spent time on yesterday. So I wanted to make it nice, basically. Okay, and then let's flash. So we're waiting for the flashing to finish, and this should be slower because we're in SPI mode and a prescaler of 4. So I think, right. This is actually kind of odd. So after it reboots, it almost immediately starts blinking. Oh man, could it be that I have if-def this with a 0? No. I was worried that this code was disabled. But it is too fast. It shouldn't be this fast. So I'm guessing that I'm reading that when I read the status register that I get happy data, basically, like too good data to be true. So let's this is a little bit convoluted, but let's remove this. Do you have the MX flash connected or easy? It's the MX flash. It's the original one. So what I'm doing now is that I am running the script that will upload. It will upload everything. It will set the magic, it will set the address and so on, but it will not actually resume the CPU. So we can do that with the GDB. So that's what we're gonna do. So when this is done, we're gonna attach with the GDB and step through the code and see what happens. Oh, I forgot something important. I forgot the exit. So now we're actually stuck here, but that's fine. So we can just there we go. So now we're attaching GDB to this, but it got really angry. Why? This is not good. One more time. Okay, we're in the reset handler, and we can actually check if the magic is correct. Oh, and it is. So that means that our registers are set. That's good. Setting a breakpoint. That seems to work. Yeah. Yeah. Okay. Is that WeChat? Yeah, it is. It is. Yeah, this is how it looks. This is how I can read your chat. It's perfect. Because I am really bad at using two screens when I'm really focused. So I will miss people writing if I have the chat on the left screen, for example. I just don't, I can't process that. So I have to do it like this. Okay, write enable. That is only writing some register, or yeah, writing one instruction. So I'm more curious about the chip arrays. It will write and it will read, and the status is OX3C. I think that looks odd. That's a lot of ones that shouldn't be there. Let's bring up the EC. No, not EC. MX. There we go. Status register. Oh. Oh. This status register is 2 bytes long. Or even longer. What? But why did this work yesterday then? Yeah, it is recommended to check the write in progress bit before sending a new instruction. Yeah. But that is what I'm doing, but I'm only reading the first byte. So how long is it then? RDSR. Okay, here's a nice flowchart. That's perfect. Start. Write enable. RDSR. Write enable latch is 1. Yeah, so maybe we should do that as well. So whenever you do the write enable command, the write enable latch will be set to 1. And according to this chart, you should actually check it, and if not, you should just try again. So maybe that is defined behavior that you should just loop until it actually latches. That's interesting. Program erase command. Write RDSR command. Write in progress is 0. And that is what we're doing here. Let me show you the code. Program. Yeah, so for each page we program, we write the pages, or the page, single page, and then we send the OX05 command with 1 byte, and we check if the LSB is set, which is supposed to be the write in progress bit. It was for the EC chip, but it might not be on this chip, which is, yeah, let's see. Okay, this is what I was looking for. So this is a table of the status register. But according to this, it's only 1 byte, so that's good. And it seems to map 1-to-1 with the other one. Because here we have the EC, and yeah, so we have the write in progress, write enable latch, write in progress, write enable latch, 0, 1, 2, 3, 0, 1, 2, 3, and then QE, quad enable, and status register write protect, right, and we don't want to do that. If we accidentally write the 1 to there, I don't know really what happens. I hope, yeah, we shouldn't do that anyway. Anyway, this doesn't make sense, because having 1, 1, 1, 1, that means that block protection bit is suddenly 1. What the heck? Why would they be that? So according to, if we can trust this, hey, I'm sorry if you have answered this already. Is there a reason you're attempting to use the NES emulator in the original firmware? Yeah, so the reason is that, first of all, it's cool to have open source, publicly available source code that you run. Yeah, right. We are not. Yeah, that's correct. There are probably other people who try to do it, but we are not. So the reason why we want to use the open source stuff is because it's open source and we don't have to care about legal issues, basically. And it's pretty fun to be able to tweak the code instead of having to binary patch and so on and so on. The list is long. Anyway, if we can trust this, this means that I have managed to somehow set block protection, which is not good. So I'm actually gonna connect another trusty hardware. I can show you like this. Yeah, I can actually disconnect this now and move it. So yeah, again, the reason why I have this, being able to disconnect this, is so I can connect it to this other device. So this is a piece of hardware called Glasgow. It's an FPGA and contains level shifters and allows me to interface with basically any hardware. So I'm using that as a Flash programmer. So let's do that. Here we go. Yeah, Glasgow is awesome. I've had so much use with it. Okay, let's move back to this. So let's see what we can do. Yeah, definitely. Shout out to White Quark. So what do we want to do? We can see if we can identify the chip. Can we speak with the chip, or is it completely borked? Okay, this looks good. This indicates that stuff is definitely working. Do we actually see if it's bad? like if it's locked. I don't think so. There's another, right, protect. This will show the protect. Oh, holy crap, look at this. I don't know how. This is scary. I have actually managed to set the protect bits. That's really bad. So shit. So stack smashing. Maybe you should be careful with my latest changes. Maybe I'm doing something stupid, or it looks like I'm actually doing something stupid. So I don't know if you can flip these back to 0. Yeah, you can. And yeah, look at this. Now I have unprotected it. So why the heck was it protected? This scares me because that means that I have messed something up that I don't understand. Like it's okay to mess up if you understand why you messed up. But if you messed up and you don't know why, that's not good. Well, shit. So I'm pretty sure. Yes, it is the STM32 Game & Watch, correct. And what we're looking at right now is that I have accidentally locked the flash with the firmware for some reason. I'm trying to understand why. So I'm pretty sure that I didn't. I honestly don't know. It doesn't make any sense. Yeah, you're right. But in this case, I don't know. I'm gonna have nightmares about this. Because if you don't have a programmer and not, if you're not comfortable changing in this stuff, then yeah, maybe you will have a locked flash. That's gonna suck. So anyway, let's erase the flash just so we don't have any old junk on it, and let's try the flash loader again, because the flash loader is supposed to work. So I don't know. So I'm just gonna move this out of the way and connect this guy again. Yeah, my masking tape is starting to wear. This hack has survived for too long. Yeah, by the way, I can just gonna show something in a second. Yeah, there we go. So, oh. I love it when Twitter does that to you. Anyway, we did a quick hack where we soldered the SWD wires to the USB connector, and that works surprisingly well. So with this hack, you can have a closed device where the case is fully sealed, no wires hanging out, no drills. And then you have this adapter where you simply break out the USB data pins and connect them as SWD wires. And with this, you can program the internal, you can program the STM32, and through that, with the flash loader, you can program the flash. So if I had that solution with this device, then yeah, I wouldn't have to worry about this with the wires. So anyway, let's see what happens when I run this. I'm just gonna, oh, I'm in the wrong project. So, all right, you probably need voltage. Okay, this looks much better. No, right, I had this change, right. So okay, check this out now. OX3 means that the write enable latch is set and it's busy writing. So I can press continue and hopefully it will finish the flashing. Might be just me misreading, but the Macronics datasheet mentions. Oh, oh, thank you for noticing that. That is interesting. Where did you see that? This is this the footnote with a reference somewhere? Because I don't see the S7 in the table. Because I don't know how to interpret this. Does this mean that you can only use this in 33 megahertz? Like you can only program it in 33 megahertz? Or was that voltage and current consumption table made when running at 33 megahertz? Refers to the first line in the DC characteristics. Clock frequency. Damn. Okay. Wow. So okay, there aren't that many. Page 64. Ah, thanks. There we go. Oh, right. This is a good good table to read. Are we looking at the same? I'm looking at. Maybe this is wrong. Because I don't see 33 megahertz here. Maybe I'm just blind. And in this data sheet, it says 108 for this one, but it has the footnote 7. Okay, now I get it. Oh, okay. So this 7 is not on this page, it's on this page. over here. Okay, now I understand. Datasheets are, yeah, always interesting. So what does that mean then? Does that mean that I can do programming in 108 megahertz, but I can only set this register at 33 megahertz? Write status register. Yeah, that seems to be it. That's really funky. Can you actually change the prescaler in the command? If anyone in the chat knows about this, now's the time to let me know. So the question is, can I have a lower speed for certain commands and higher speed for other commands? This was interesting. I didn't know this was normal. But actually, am I using this, the write status register command? Because I remember I used it before, but in order to enter quad mode, but I don't think I do that anymore. So this is the command 01 hex. So I'm just reading. No. Okay, I think we're safe. So yesterday I was experimenting with enabling quad mode by writing to the status register where I set the quad mode. But today, with the code we have today, I'm not actually sending the instruction OX01. So I think we're actually safe. But that's a really interesting thing you found there. So thanks for finding it, but I think we are okay. So anyway, let's halt the CPU and yeah, check it out. Now we have a beautiful counter. Everything is working again, but there is still a mystery. Like for some reason, which I cannot explain, we enabled protection of all the 4 banks. I don't understand why that happened. So now we can actually, I'm gonna leave the prescaler or whatever it's called. 4, yeah, as 4, because it runs slower, but it will be safer. And actually, I'm gonna go into quad mode again because there is no real reason to use SPI mode. Make, let's do it again. All right, I need to change the script again. So like so will be fine. And yeah, we can. Okay, the dongle got angry. Okay. All right, it's done. And let's debug it again. No, now it's broken again. So this is not good. I wanted to focus on other things and not this. So it seems that I have broken quad mode on the flash tool, or in the flash tool. That is bad. But in order for this to move forward, let's just keep it in SPI mode, and I will fix that later. So I'm just going to revert to SPI mode and yeah, because I want to code on the emulator stuff and not do this. So otherwise we're going to be, I don't know. This stuff is really hard to do on stream because I need to focus a little bit more and it's hard. It's hard to focus. Okay, we're back on track. And I'm just gonna double check. Yes, we can read and it looks sane. Time to move on. So let's go back to this project and see where we are standing. So in the make file, we are running the Super Tilt Pro. Perfect. In the NES integration, we have the DMA stuff, DMA rewrite thing. Cool. And that should, I mean, we had it working, and this stuff is commented out. Yes, perfect. And this is the APU stuff that didn't really work, so let's not do that right now. So I'm just gonna make a sanity check and do a clean build and just see if it still works. And also we can see if the microphone is still working. Just gonna unmute. Yeah, so that seems to work. So, oh, I got some error. Why? Because I have OpenOCD. So whenever you're debugging like this and you see that you get some strange OpenOCD error, just double check that you're not running OpenOCD somewhere else, because it's easy to do that. Okay, now it's programming, and because this is actually a quite big ROM, this takes a while, unfortunately. But yeah, it's not that slow. The slow part is to actually send it to RAM. Okay. I am getting worried about this. I mean, this worked. Just gonna try something. So the reason why I have this block in an if def is because I can disable it, and then I can simply flash this program. Alright, I need to disable this as well. So what this now does is that it initializes the SPI flash and it enables the memory map mode. That enables me to look at the flash. And yeah, this looks actually sane. So what I can do now is that I'm gonna go over here and I'm gonna do telnet and do a dump of the whole external flash. Let's just, right, the files are actually gonna end up here. Yeah, this will be fine. Yeah, so now I'm using the flashloader implementation of the memory map mode. to dump 1 megabyte, the whole flash, into a file. And then in a few seconds, we're gonna diff this file with the external flash from this project, because it's supposed to be the same. So this file and this, and they differ. Okay, thank you. Damn it, what is the argument? -w -I. Then let's see how much it differs. It could be that it doesn't differ that much. So this is kind of interesting. This means that it is actually identical. So this means that the X here means that the left file, the file on the left, is not that long. So these bytes do not exist. But these bytes, on the other hand, exist in the flash dump because I've dumped the whole flash. So this actually means that the flash contains the correct data. So I'm starting to think that in the emulator codebase, that the code that initializes the flash memory is not correct. So in order to verify that, we can run OpenOCD. First we need to make flash. Right, we need to kill that. Make flash. So now we're flashing the emulator, and as you can see it's borked, but let's try to understand why. So it's full of 888888888. Okay, but as you just saw, when I ran this code base, we got the correct data. So that means, or indicates, that this code base works better than this. Also, I'm running this in SPI mode, so what I'm gonna do now is I'm gonna take the whole Flash implementation and just move it to this code base. Or copy it, basically. And then I need to adjust this a little bit. So let's copy that as well. And actually I should move this probably honestly I don't know. Maybe here is the best place. After we enable the caches and before we copy from the external flash. Yeah, that's probably fine. So time to make clean and flash. Yeah, so this will probably not execute correctly because the external flash will have pointers that point. Yeah, so this is completely borked, but it's a good sign. This means that that the code actually works. So what happened was that it executed code that got past this point. So we got actually correct data, but then it actually sort of crashed or glitched because the external flash has pointers into the internal flash that doesn't match anymore. Okay, this is actually a little bit worrisome. You can't hear this probably, but it sounds it got stuck in some horrible state. Probably because it's in a hard fault or something. Let's see where it is. Yes, hard fault. So, yeah. Why does it hard fault? I have to... Oh my god, this is really annoying. I need to disable the sound because it's making me crazy. Fortunately, you can't hear it, but if you could, you would have been really angry, I guess. I need to kill it. Oh, thank you. So, audio in a circular DMA buffer with junk, it's extremely annoying because it just loops with a glitched sound. It's just horrible. Anyway, so something is wrong. We don't really know why. What was the new Skrillex song? Yeah. Exactly. All right. I think. Right. I think the length of the ROM is incorrect. This is not correct. It should be this. There we go. By the way, one of the Skrillex albums is officially regarded as a mosquito repellent. Okay, nice. All right. Oh, it's borked. It's borked. So why the heck is it so borked? So I'm gonna break in main and all right. Okay, looks good. So I'm gonna dump and then I'm gonna diff it. So it could be again that I've broken something. I mean, it's likely, or I have most likely broken something, but I still don't really understand why. Could be this. But this size, if I'm not setting it, it should be 1 meg. So yeah, strange. Okay, the dump is complete. Let's diff. They differ because ay, this does not look good. Check this out. I would say this looks like signal integrity issues because I get single bit errors here and there. 3C instead of 40. Seems like the one is offset with one position. Let's visualize it. OX40 looks like this, and OX3C looks like this, actually. It's not just one, it's 1, 2, 3. It's what? This does not make sense. But interesting. So what happens if we dial down the prescaler? Where do we do that again? Yeah, let's dial down the prescaler with 4, and now we can actually flash it like so. Because when you change values like this, no, it's also borked. Crap. I don't understand why. This is depressing. Okay, making another. Number 3. Did I actually build? Yeah, I did. Yeah, it built main again. Okay, cool. Let's. They will obviously differ. No, same thing again. This looks like it was flashed with the incorrect data. Which means it was flashloader that made the mistake. Or there is something else going on that I don't understand. So actually, there isn't that much that differs. Like, the external flash is not that huge. Wait a minute, does this make sense? So, the external flash is supposed to be quite big. OXB4160. Oh. B4160. Okay, so this is proof that it has the correct size, but I really don't like this part. Like, what the heck? Do we have stuff in the flash? But it's probably because, yeah, I probably know why. Because we're actually programming the whole RAM area, and it contains uninitialized RAM. So this part is not that strange. We could optimize that, of course. But why do we have these errors? So what we could do is that we use Glasgow again and dump the flash just to verify that, like, what is the actual truth. Because with Glasgow, I trust that code with my life almost. It is very nice. And also I'm running it very slowly, so I don't expect any signal integrity issues to occur. So let's read and call this yeah, so I'm gonna read the full flash. Then we can diff this. Okay, this proves that the flash integration can read from the flash. The issue is with the programming of the flash. Or maybe right. Yeah, what we can do actually is to program it with this, just to see if the program works. First we need to erase the chip. You can also do the program erase, but I trust this more, because this way I'm certain that the whole chip is erased, and then I can program it page by page. So this is a little bit slower, but it's fine. It's running at 3 megahertz, I think. But yeah, safety first. Cool. Now that is done, we can move this aside and connect this again. And let's see what happens. Yeah, it seems to work. So again, the issue seems to be the flashloader, which is really annoying. But I'm starting to think that it's a signal integrity issue, but I don't understand it. Let's prescale it even slower. 8. And then actually I'm gonna do what I did before. I made a random file, and then I flash that random file, because a random file is much better than a counter, because a random file will have a high entropy and lots of bits changing, whereas a counter contains a lot of bits with the same value. Okay, so it blinked really early, which is strange. So could it be? I have it in SPI mode. This is... Oh, this is the issue. Oh no. Oh my god. Okay. This is what we in Swedish call skit bakom spakarna. That, yeah, pebcac, basically. So let's do this again. Okay, this is embarrassing, but yeah. So the issue was that I had left the if 0 on the actual programming part, so it never actually erased the chip. Yes. Here we go. Yes, now the flashing actually takes time, which it should, which is good. Okay. Yeah. Maybe I should open a window and get some fresh air. 1 second. Yeah, and as you could hear, it works perfectly. But did the sound good? I actually I didn't listen that closely, so let's try that again. I mean, it sounds like there's a cyclic pattern of bad noise. It doesn't sound perfect. So let's move on to the code and do what I wanted to do from the very beginning. Which is to fix the audio. Here we go. So does this even build? Yes. Okay, perfect. So this should basically mute everything except for the triangle. Let's mute the triangle again as well, and then we can build this just to see if this does what I think it does. Yeah, no, this didn't make any difference whatsoever. I still hear the music, which sounds very nice, but I would expect this to actually have an effect. Let's try to understand a little bit more how it works. Just gonna turn it off. So, how does the APU work? For each sample we want to get, we increase an accumulator. What does this actually do? Let's take the triangle, that was easier. So this is the ADSR, I guess. Decay. Triangle enabled. Oh. Oh, okay. So the output volume is being set by this function because it is performing the decay from the ADSR, I think. Yeah. So, let's see if we can do something interesting here. Maybe we should just set the enabled bit to 0. And then focus on one instrument or one oscillator. And then we can set the output volume to be, what kind of field was this? In 32. Okay. It's hard to know how large these values should be. I guess we can try something large. -1. Yep, it's super loud. Okay, there's definitely sound coming, but I think something is up with the other registers. So let's try to understand a little bit more how it works. So this performs the ADSR, and then, alright, there's a channel 6 as well. Does this even build? No. Oh, never mind that then. Yeah, I don't know. This is, I mean, I'm going at this from the completely wrong direction. I'm trying to reset registers here, which is probably not the right way to do it. So how does this actually work? Oh, this looks nice. Okay, so these are all the registers it can hold. Well, I just want to have a continuous sound from the NES. Maybe it's not possible to do this way. It's a bit annoying. Let's try something. Oh, I forgot to remove this print. Oops. Yeah, check this out. So, because I am waiting for the DMA, which I do here, I get a perfect 60 FPS with no skipped frames. Yeah, because I removed the frame skipping, but I get perfect 60 FPS because the audio is running at that speed. So that's pretty cool. Yeah, I'm just waiting for the DMA state to either go to middle or half full or full. So at least that part works. That's nice. Just a little bit worried if I messed up the update of the audio. So if we start to think about this, so We wait until the DMA state changes, then we continue. Fine. So for example, it goes from 1 to 2. And then during the next game loop, it will stay 2 until we get here again, and then we wait for it to become 1. So while it is 2, we should update the second part, because even if this note doesn't make much sense, so while this state is 1, so when we reach this point in the middle, we will set the DMA state to 1. What I miss? Well, lots of stupid mistakes, but I'm back on track. I can flash and I can work, so that part is good. So right now I'm back doing the audio stuff, and I have audio working. I was trying to write to the APU directly to create a continuous tone, but I think that is a little bit hard to do while there is music playing. But actually, now that I think about it, I can actually mute. I can mute the music in the GUI or in the game, and that way I can play a tone myself, I think. So we can do, I don't know what unit frick is. No idea what this unit is. It shifts something to the, okay, it's 16-bit. So yeah, say a nice frequency. Let's say 440. I don't know if it's hertz or if it is a different unit. We'll find out. So we can change this, I think. Let's do like that. And I can change this. Same with this. And then there were some other things. Adder, hold note, counter started. I don't know what those should be, but I guess I can poke at those when it's muted. Yeah, maybe that's, yeah, I can do that. Okay, cool. Let's try this. So now we're gonna flash this, and then I'm gonna run it. I'm gonna mute the sound in the game, and then I can, with the debugger, change these values and also the other internal state values until we hear a continuous sound. Yeah, I'm gonna do that. Let's try it. Okay, and flash. Yeah, so there is some sound for some reason. Let's go into the game and turn off the music. So now it's supposed to be silent. It's not really silent. It sounds a little bit strange. But let's go into the debug. And then we can change. Let's see if I can. Yeah, okay. So these are the internal state of the triangle oscillator. Nice. So what actually changes. Counter started false. Okay. So let's start it. I don't hear anything. Maybe a linear length. No. I guess I need to do something to start the yeah, right, because the rigs are probably not correct. Okay. Okay, so the way it works. So the CPU calls APU write, I think. Yeah. So whenever you get a sound block, it will write to the APU. Is this part of the state load? Okay. What is actually... I wonder how this actually works. Like whenever you play music, what is actually going on? When are these bits being set and so on? I would assume it's the APU write, but I don't find any references to it, so it's kind of strange. APU process, that's what we're doing. Let's set options. Nobody does that. Okay. Maybe this is done with the pointer magic. Oh, what is this? Ah, okay. This is interesting. Okay. Right. Okay. So this is what's actually sort of executing the audio chip. And what does that do? It will increase cycles, check some state. Okay. Okay, I don't really know. Let's go back to the code. All right, it's flashing. And I'm gonna do a recording again. There we go. And stop. And then normalize. Yeah. There is like a continuous rattle, or however you can explain it. So the period is 16.6 milliseconds. So can we see something periodic with that period? So for example, these two spikes, they look really suspect to me. Can we see the difference in time? Yeah, okay, so let's take a Python 9 to 1. 34. Okay, what is 34 divided by 2? Yeah, 17. That is suspect. Are you following? So my theory, so one buffer is 2 times 16.6. This is how many milliseconds one DMA buffer is. And we can see a periodic stutter, a spike that occurs with that time. So you can see this spike, you can see this spike, you can see this spike. So I'm willing to bet that this is going to be exactly the same if we take from here to here, we take 952.920. Yeah, check it out. So this is our issue. So there. So that we get a continuous stream, and we do update the audio, but the transition when the audio loops is not nice. Why? So I had some issues with this during bring up, where I made a tone generator, just a for loop, and it didn't sound well unless the frequency was something particular, like it had to be evenly divisible by some power of 2 or some factor of the buffer. I don't remember. I'm starting to think that that's our issue here as well, that maybe we're actually filling the DMA buffer properly and we don't lag. The issue is in the DMA integration. So let's take a look at that. Perfect frame rate waiting. Yeah, so check it out. We can, with some luck, this is our log from our previous run. So as you can see, the first frame will always be a little bit messed up. So don't care about that. But check it out. It's 60 FPS. Perfect. All the time. So I think this is nice. Actually, this is not good. Why? Maybe I forgot to... I forgot to remove this code. Holy shit. Why didn't I remove this code? Again, facepalm. It happens. So, what this log told me, just so you understand what I saw, was that this proves that we're actually calling HAL delay with 1 millisecond every frame. That's not good. But it doesn't explain why we have the stutter. This will improve things a little bit, but it doesn't explain everything. Right, let's flash a little bit more. So I'm going to make a new recording. Okay, so going back here and selecting this part, making a normalize. No, it doesn't sound perfect. And let's do the trick again, where we check the time delta between the spikes. And this looks like a spike, but yeah, I'm gonna take this spike. So let's see if it's a factor of 16. 1 to 8, 9 to... Okay. I don't know, this is not as convincing. So what I'm looking for are these repeating spikes, like these. Yeah, so this is the 60 millisecond again. But yeah, again, we can go back to the print and see. This time we didn't skip anything and we didn't skip anything. Okay, so this is better. Yeah, Super Tilt Pro, that's right. Mm. So what am I missing? Are we doing something wrong in the audio buffer? I mean, we can try to just disable this for now. What's the sample rate you're recording the audio at? It looks like 11 kilohertz. Yeah, you're right. I don't know why it says that here. Let's move it to 48 because I don't think it is actually that bad. Testing. Okay, it is actually that bad. Why is my project setup so bad? Every time I use Audacity, I get a brain issue. Okay. Testing 1, 2, 3. Okay, much better. So let's do this one more time. Nice. And let's normalize. Yeah, now you can hear the pops very clearly in the recording. I'm sure you can hear it in the stream too. It sounds like a buzz, like a low frequency buzz. I mean, basically it's 60 hertz, extremely short PWM or PWM. We cannot, but it's probably for the better. I mean, it sounds almost nice, almost perfect. Like, let me just show you. So, I mean, it's not that bad. You could hear that, right? Yep. Okay, good. So it has like a PWM that runs at 16 hertz. So essentially, you're listening to a square wave that looks like, yeah, like this, with an extremely short on period. This is basically the waveform we're listening at, and the frequency is 60 hertz, 16 milliseconds between. And here, this looks like a proper waveform, right? But I was trying to like get a proper, like a scientifically being able to see, okay, here is the glitch, and this is how long the glitch is. Because here it looks like there's like an extra spike here, extra little spike, and there as well. And then we can take the delta in time, and we see that, okay, 737 minus 719. This time it's 18, which doesn't really map to anything. So maybe it's a little bit hard to see, but when you listen to it, you can hear it clearly if you listen for it. But anyway, we know it's there, so we don't have to sort of prove that there is a problem because we can clearly hear the problem. So let me just increase the spectrum. Let's go to 16 kilohertz. That's probably good. I was hoping to see something here, but I don't. Okay, never mind. Let's go back to the code. So what I'm gonna do now is I'm gonna initialize the buffer with let's see here. As you can tell, I like to copy paste code because it's usually faster until it's not. And yeah, so let's do some math. So this buffer is this long. So yeah, if we just take the accumulator and what will the frequency be then? So it basically happens each frame. Yes, or yeah, the question is if it's on each frame or each audio frame, like each DMA frame or each visual frame. Because if you remember, I made the DMA buffer twice the size. So I guess what I was looking for was if this stutter comes at 16 or 32 milliseconds. Now that I think about it, so the fact that I seem to see something at 16 indicates that it is actually the other code that's broken. Again, maybe perfect FPS wait is the case. Yeah, so what I'm doing again is this. So in the end of each frame, I am waiting for the DMA to reach its next state, which is either that it came to the middle, half full, or that it reached the end. Sound output is probably tied to frame rate. Yeah, it is. Because when we initialize the emulator, we pass the audio sample rate, and that in turn sets a bunch of registers or variables. And as init, it initializes the APU with the sample rate, and the cycle rate is then derived from the sample rate. And I believe that this is used in other places. Okay, this seems to be mostly be used by the APU. Let's see if this is used anywhere. No? Okay. So the question is, the CPU, when that is being executed, which we do in the main loop somewhere. Here, let's emulate. Yeah, so this is the main loop. We do a render frame. And how does it know how much it should render? Scan lines per frame. Okay, where does that come from? That comes from this. Right. Okay. So, right. Because... wait a second here. If I don't misremember, this ROM that I'm playing is actually a PAL ROM, which messes up everything. Because I have hard-coded a bunch of stuff to NTSC. But because I'm streaming, I don't want to play any copyrighted games. I guess it's still under copyright, but less hostile than other game vendors. But still, it should only lead to that the sound is off pitch Like if I'm playing a if I'm playing a PAL game in 60 hertz, that shouldn't be that bad. It should just sound differently and run faster than it's supposed to. Yes, anyway, it renders the frame, and I think I somehow broke my game watch while trying some RDP things. That's really sucky to hear. I hope you're wrong. I really hope you're wrong. Yeah, I don't know how. Same. The only thing I can think of is if you entered RDP2 by mistake. I can't think of any other way to actually brick it. Or there's one other way if you manage to sort of use the GPIOs for the SWD pins in the firmware or something too early, but I don't think you did that, so maybe, yeah. Oh, I don't remember those by heart. Is AA RDP0? Yeah, okay. So, yeah, it says here in the datasheet, RDP level 0, option byte value AA. Yeah, and CC is level 2, and any other value is level 1. So this is actually pretty fun. So if you manage to glitch, if it is in CC and you manage to glitch 1 bit, then you automatically get into level 1, I guess. Okay. Strange. Maybe the Game & Watch is just sad. Oh, nice. Nice. Cool. Yeah. I really want to bump up my glitching experience. I just know of it. Oh, yeah. That's what you did with that one. Right. Cool. Yeah. I just don't have any products to glitch. I don't know what to hack. This didn't need that sort of hacking. Right. Okay, so this is how it works. So it checks the file name and looks for European or Australian strings and sets PAL. Otherwise, it's NTSC. Memory protection. Yeah, exactly. But yeah, since you read OXAA, I don't understand. It's really strange. Maybe the firmware that's. I mean, after you change it, it will flash. I mean, it will erase itself. And yeah, I can't think of anything. I mean, I'm pretty certain you have already power cycled and tried all the standard things 10 times. I don't. Well, don't you have to unlock it first? Like you need to send sort of write enable. Because I had quite some issues when I unlocked mine. Because I did my unlocking with OpenOCD and it was a pain. Okay. Yeah, I think I did something similar. Okay, maybe I shouldn't do that in that screen. let me see if I can find my script. Okay, thanks for hanging out. Yeah, it would be nice to have it like perfect. All right, let's see if we can improve this a little bit. I mean, we can still hear some sort of noise, but yeah, let's go back to the code and do like, so this will be 1600, right? So 1600. We can shift that a few times. Okay. Right, I can actually take this code, move that, because this is getting stuck because of the external flash. But I want to iterate quickly, so I don't want to have to bother with that. So let's just do that here, and do like that, do like this. Oh, okay. All right, I need to multiply this. Okay. How bad is audio? No, audio is pretty good. I can show you. Yeah, I'll just make a quick demo because this stream is getting boring, I guess. So let me just enable sound, disable this, and do that, and go in here. Yeah, So my camera setup is not optimal. The backlight is pretty strong, but I can see if I can get it, if I can show it a little bit better. And I can also enable the sound. Yep. Okay, and then we go there. Oh, did I break it? It's so easy to break things when you change stuff everywhere. Because now, yeah, right, I forgot this. Okay, just a few seconds, any second now. Alright, let's see if this works. Yeah, I don't know. I've actually never played this game. I've just opened the menu. So I'm sorry for the bad demo, but that's basically it. And that's how bad the sound is. So it's like not perfect, but it's not horrible either. But it could definitely be better. Audio also pitched down from frame rate dropped, but that's normal, I suppose. Well, let's see if the frame rate actually dropped. So according to this, I haven't seen any dropped frames. So I don't know. Yeah, I mean, ideally I want to show some more famous game, but I don't want to do that on stream because I don't want to deal with potential issues with that. But let me just say that, yes, your favorite games definitely also work. Babel, yes, all right, let's do that. So how do I find that? I trust that this is okay. It doesn't really say anything about license. Maybe here on the issue page. Short game, room file. Oh yeah, I read about this. Well, I don't see any licensing information, so I guess it's fine. Let's just do it. So this one, I guess. So we go into rooms, NES, Yeah, and do like this. And morphcat is reachable on TWI, and I can be asked. Nice. So are these demos for demo parties? Alright, let's see if it breaks. Okay, I think maybe the emulator is not that perfect. Yeah, sorry for the focus. So let's check the frame rate. Because I believe this could be, because of the bubble effect, it looks kind of, it might be a little bit heavy to run perhaps. So let's just switch back and do the make, debug, and printf. Yeah, check it out. So 60 FPS, no frame drops, it looks perfect. Or actually here in the beginning there was a tiny something wrong. But I think it looks pretty good. Yearly NestDev competition. Okay, cool. Do you still hear the crackle? I don't think I did. Yeah, let me enable the sound. It sounds pretty good. It sounds pretty good. Maybe, are there any chip discs for NES? I'm really bad at this, but it would be really nice to play some sweet chip tunes. Maybe from... I mean, playing a compo can't be... I mean, that should be fine, right? Use PAL NES to run this, or select PAL. Okay, so I'm running at NTSC, but that just means that it will run a little bit faster. Oh, there we go. Okay, let's try this out. This is exciting. Demo compos are always fun. What was this called? Hi. Okay. High hopes will break bad on NTSC timings. Okay. Well, let's do it anyway and see how bad it is. I'm curious now. So now I'm using the other microphone. Oh, what the heck? Okay, I forgot something quite important. Didn't change this one. What was it called again? High hopes. Did it actually rebuild? Yeah, okay. There we go. Okay, that broke spectacularly. Okay, and this is a NES ROM as well, I hope. All right. There wasn't that much of music in that. I mean, there is some music, but it would be cool with something with more, like a chip disk with lots of music. Because here it sounds like it could be just the ROM glitching a little bit, or it's hard to say. Really hard to say if if the sound is good or bad. Maybe I can filter a little bit here. Okay, not that much, but Wow, does this run on the NES? This would be pretty cool. Okay. So it's not actually running on the NES. I have to double check. Probably need to listen to it running normally to get familiarized. Yeah. So, I mean, what I'm actually looking for is like a proper tune. Family Tracker. That's also a Win32 tool. Okay. But is there something like LSDJ for the NES? I don't have any clue. Because if there was like a onboard tracker, that would be really nice. Because then I could simply use that tool to just play any tones I want, and it would probably be able to play some awesome music as well. Because I'm really an emulation noob. I don't know anything about NES emulation. Are there any trackers that run on the device? Because all of this looks like tools for Windows, MS-DOS, Amiga, Windows. NES. Okay, this starts to get interesting. There was NTRQ, Google Neil Baldwin. Okay, cool, thanks. So that is the drum synth that I saw on the other side as well. This sounds nice, I guess. Seems dead. Oh. Okay. Let's see what that is. Oh, it's open source even. Or no. Oops. I don't know. Rupa. Oh, so this is an actual chip disk. This is exactly what I'm looking for. Thank you. Thank you. Perfect. And be boom. Okay. All right. Let me just try this ROM first. Oh, okay. Perfect. Yeah, I don't know. Maybe. Actually, oh no, what happened? I forgot to say. Okay. Yeah, I mean, we do have the Game Boy emulator as well. It would be really cool to run LSDJ, because there is so much really cool music being made on that platform. So that would be really nice. Okay, here we go. Okay, so this sounds pretty bad, I think. It sounds like it's stuttering and clipping. This sounds pretty good, don't you think? I'm gonna record this. Yeah. Okay, so here it actually dropped. The frame rate actually dropped. And then here it went up again. But yeah, you're right. It didn't sound perfect. Oh, sorry. Thanks. Thanks for reminding me. Yeah. What can we do about that then? So I'm still kind of interested about playing a sound like this. Just making a tone and listen to it. Okay, this is weird. Probably forgetting something. So what I'm doing here, I just want to create some noise and listen to it, but for some very strange reason, there is no sound at all. I don't understand. Because this happens before anything, basically. I mean, sure, I can move this down a little bit to this part. Oh, okay. That's not so strange. Then, okay, so okay, programming 101. What am I doing wrong here? I want to fill the audio buffer with data that changes over time, so I get a frequency. Why doesn't that happen? So, okay, I have the same value. It's still the same value. How can that be? I mean, am I so... what? This should clearly increase. Why isn't that stored? What is going on here? Ah, what? If I do like this is the simplest loop ever, right? Okay, now it works fine. So let's multiply by something. I guess I'm getting tired. I don't hear anything. I mean, I expect to hear something. No, I don't know. I think it's time to wrap this up. I'm not really getting anywhere. So we have made the sound better, but it's not perfect yet. I will try to make it perfect later, I guess. We found a bunch of bugs. We fixed a bunch of bugs. So that's good. Yeah. All right. Let's wrap this up. So thanks everyone for joining today. It's been fun. It's been helpful, and it's always fun to get comments and helping me out when I get stuck and so on. So yeah, it's been really nice. Maybe automate the room loading. Yeah. So it's like a classic. I'm lazy, so I always go for the laziest solution, which is usually to do what works and just do it over and over again. But yeah, for sure, make. I should definitely script it. Yeah. I should have done that a long time ago. Um, and it's not much. It's only like three things that needs to be done. So it's really. I've just been too lazy for my own good. But it's how it is. I should do that. But eventually, we should enable the on-screen display and you know be able to load multiple ROMs and be able to yeah ideally have a file system perhaps even. But yeah, I don't want to gold plate too much. I just want to get like a good quality integration that has good audio, good visuals, no frame skips, and so on. That would be really cool. So that's the goal. That's my goal at least. Like when I release this, then I'll be happy to let other people continue, for sure, definitely, because I don't think I will have the energy to like properly maintain this. Um, but it's fun, so and I like to share the experience. Like this is this is what it's like. Like you just spend sometimes hours bashing your head against the wall and trying to understand why isn't this simple thing working, and then other times it goes super fast and you just code and stuff just works. But yeah, sometimes it's like this. You get these nasty issues that take time to fix and so on. But yeah, anyway, let's wrap this up. So thanks again for joining. And yeah, again, I'm kind of bad at holding schedules, keeping schedules. So even if I try to announce a few days in advance and say, oh, I will stream at this time, then yeah, I might not be able to keep that schedule. So I'll probably just shout out and scream, okay, it's time, and stream. All right. Thanks, everyone. Bye.